Let's discuss the questions on the JEE Main pattern exercises for continuity and differentiability. The first question says that the function is defined from collection of all reals minus singleton 0 to the collection of all reals like this. This function can be made continuous at x equals 0 by defining f of 0 as what? So basically if you talk about f of x is given to you as 1 upon x minus 2 upon e to the power 2x minus 1. You can make this function continuous at 0 by defining f of 0 as what? F of 0 should be defined as limit x tends to 0 f of x. If this happens to be true, in that case I can say that the function f is continuous at x equals 0. But for this we need to first compute limit x tends to 0 f of x. What would this be? Limit x tends to 0 f of x is actually limit x tends to 0, this function. What is this? E to the power 2x minus 1 minus 2x whole upon x into e to the power 2x minus 1. Now you can just use the very expansion of this exponential function. What is it? E to the, or I should write 1 plus 2x square by 2 factorial plus 2x cube by 3 factorial and so on minus 1 minus 2x as it is. I am just using the expansion of the exponential function, and then in the denominator as well this is 1 plus 2x square by 2 factorial plus and so on minus 1. 1 minus 1 gets cancelled, 1 2x minus 1 minus 2x, everything gets cancelled out. What you are left with is limit x tends to 0, this becomes what? 2x square by 2 factorial, then 2x cube by 3 factorial. So basically 2x square can be brought out common. You are left with 1 by 2 factorial and then rest of the terms have x term in them. How? This will be 2x cube by 3 factorial. So 2x square has been brought out. 2x is left by 3 factorial and then and so on. Fine? Whole upon, if you see carefully, this is 2x square, right? This is 2x into x, 2x square plus 2x whole square into x by 2 factorial and so on. So what I do in the denominator is I take out 2x square common. I am left with 1 plus. So from here 2x square has been brought out common. So you are left with 2x by 2 factorial and so on. Clear? You are left with 2x square has been brought out common. So 1 2 is left, 1x is left and therefore 2x by 2 factorial is left. Rest all the terms are going to have at least one x term. Here also at least one x term will be there in all the next terms. So you can see 2x square gets cancelled. You are left with 2, 1 by 2 plus 2x by 3 factorial plus and so on whole upon 2x square is cancelled. You are left with 1 plus 2x by 2 factorial and so on. Now see, as limit x approaches 0, this complete thing becomes 0 plus 1, that is 1. So denominator is 1. This complete thing becomes 0, so you are left with 1 by 2 plus 0. So eventually what you get is 2 into 1 by 2 whole upon 1, which is 1, and therefore the limit that you get for fx as x approaches 0 is 1. F of 0 should be equal to 1 for f to be continuous at x equals 0, and therefore option number B is the correct one. Moving on to the next question, we have if f is a function defined from collection of all reals to the collection of all reals like this, then compute the value of this limit. So what is the value of this limit? Let's see. It is limit x approaches to 2, fx minus f of 2 upon x minus 2. So my fx is this. If you simplify, see here x is approaching to 2, so I cannot take these values. F of 2 I need directly, I am going to plug in 1 over here. I am wanting limit x tends to 2 f of x. Now if you simplify this, what you get? You have x square minus 3x plus 2. Right? And in the numerator you have x minus 2. Okay, so this becomes what? This is x square minus 2x minus x plus 2, right? So this becomes x minus 2 whole upon x, x minus 2 minus 1, x minus 2. So eventually you get x minus 2 upon x minus 2 into x minus 1. This is 1 upon x minus 1. Okay? So basically your f of x is 1 upon x minus 1. Now plug in place of over here. So this is 1 upon x minus 1 minus f of 2. F of 2 is 1 whole upon x minus 2. 1 upon x minus 1 minus 1 whole upon x minus 2. So what you get is 1 minus x minus 1, or I should write 1 minus x minus minus plus 1 whole upon x minus 1 into x minus 2. So this becomes what? This is 1 minus x plus 1. So this becomes 2 minus x whole upon x minus 1 into x minus 2. I can write this as minus of x minus 2, right? And so I'm left with minus 1 upon x minus 1. It is actually limit x approaches to 2. So as x approaches to 2, I get just minus 1 as my answer, and that is the required limit. Clear? Easy enough question. Next question is fx is sin x by x when x is non-zero. What do you think is going to make this function continuous at x equals 0? This function will be continuous at x equals 0 if f of 0 is defined to be equal to limit x tends to 0 f of x. So what is limit x tends to 0 f of x? This is pretty simple. Limit x tends to 0 sin x by x. You know that as x approaches to 0, when x is very, very close to 0, sin x, graph of sin x is almost same as that of the identity function. So sin x approximately becomes equal to x. So x upon x gives you 1, and this is how, this is the limit that is equal to 1. So limit x tends to 0, f of x is 1. You should actually define f of 0 to be 1 if you want that your function should become continuous at x equals 0. So for fx to be continuous at x equals 0, f of 0 should be defined as 1. Clear? Next question says if f of 2 is 4, f dash 2 is 1, what is the limit of this expression? Let's calculate. What is the limit of this expression? This is limit x approaches to x into f of 2 minus 2 f of 2 plus 2 f of 2 minus 2 fx whole upon x minus 2. Clear? Now this becomes what? This is limit x approaches to, you can take out f of 2 common from here, you're left with x minus 2 whole upon x minus 2 minus, let me write, plus limit x approaches to 2 minus 2 f of x minus f of 2 upon x minus 2. I'm just simplifying the expression, nothing else. So this gives me just f of 2. This is minus 2. Limit x tends to fx minus f of 2 upon x minus 2, which is what? F dash 2. F of 2 is given to me as 4. F dash 2 is given to me as 1. 4 minus 2 gives me 2. And therefore the answer of this expression is basically nothing but 2. Easy enough, just need to manipulate it accordingly so that you can use the very derivability definition as well. Now moving ahead, we are being asked the domain of the derivative of this function. So let's understand the function first. There are mod signs involved, and therefore we need to open the very brackets up. So you have fx equals what? Let's see. So you have tan inverse x when mod x is less than or equal to 1. Tan inverse x when mod x is less than or equal to 1 means when x is lying between minus 1 and 1. Only then mod x is less than or equal to 1. Then you have when mod x is greater than 1, that means x is strictly less than minus 1 or x is strictly greater than 1. When x is strictly less than minus 1, then mod x, x is negative, so mod x will be minus x. So this definition will be 1 by 2 minus x minus 1. Similarly, when x is greater than 1, that means x is positive, mod x is x, so you get 1 by 2 x minus 1. If you carefully observe individually in these ranges, these functions are continuous as well as differentiable, right? But the problem is at these points minus 1 and 1. Let's check at these points the functions are continuous or differentiable or not. That is what is going to help us to define the very domain of the derivative of this function, right? So first of all, let me talk about x equals 1. Now limit x tends to 1 from the negative f of x. What is this? So from the left, x tends to 1 from the negative. It is tan inverse 1, which is pi by 4. And limit x tends to 1 from the positive. X tends to 1 from the positive is 0, which is not equal to pi by 4. That means f is discontinuous at x equals 1. Not continuous at a point implies not differentiable at that point. So function is not differentiable at x equals 1. Similarly, if I talk about the next interrupting point in the situation, which is minus 1, limit x tends to minus 1 from the negative. X tends to minus 1 from the negative. So x tends to minus 1 is going to make it 1 minus 1, 0. And limit x tends to minus 1 from the positive. Limit x tends to minus 1 from the positive is going to give you tan inverse minus 1, which is minus pi by 4, clearly not equal to 0. Again discontinuous at x equals minus 1 and hence not differentiable at x equals minus 1. So my function basically is continuous and differentiable at all the points on the real line except 1 minus 1. So the domain of the derivative of the function will be r minus 1 and minus 1. Clear? So basically I am indirectly concluding the result because I am using the continuity scenario to get to the non-differentiability of the function at the 2 points. Now the next question says if alpha and beta are basically the discontinuity, points of discontinuity of f of x. Okay. Where fx is this, then the set of values of a for which the points alpha and beta and a comma a square are on the same side of this line is what? So first of all, what is f of x and what are the points of discontinuity for this function? F of x is given to you as 1 upon 1 minus x. Now this is not defined or not continuous for x equals 1, right? So f is discontinuous for x equals 1. So point of discontinuity of f is x equals 1. If I talk about f of x, is 1 upon 1 minus 1 upon 1 minus x. This is equal to what? 1 minus x whole upon 1 minus x minus 1. So this happens to be x minus 1 upon x, right? And then this is not defined for x equals 0 in the denominator, right? This was 1 minus x upon 1 minus x minus 1. So this is 1 minus x upon minus x or x minus 1 upon x. Then you have f of x is what? 1 upon 1 minus x minus 1 whole upon 1 upon 1 minus x. So this gives you basically 1 minus 1 plus x, which is just x, and these two things gets cancelled out. So you are just left with x, which is defined for every real number. So basically from here to here we can see f of x is actually x, which is going to be continuous only for x not equal to 0 and 1, for all real numbers except for 0 and 1. So points of discontinuity are 0 and 1. I get alpha is 0, beta is 1, right? F of x is x for all x not equal to 0 and 1. For these 2 points this function is discontinuous. Alpha is 0, beta is 1. Now it is saying that alpha comma beta, which is I am saying 0 comma 1, and a comma a square lie on the same side of this line. That means what? 0 comma 1. So in place of x you put 0, in place of y you put 1. So you get 0 plus 2 minus 3 multiplied by, in place of x you put a, in place of y you put a square. What you get? A plus 2a square minus 3. This will be positive because both these are lying on the same side of the line. Now when you have these two things with you, you basically get negative of a plus 2a square minus 3 is greater than 0. That means a plus 2a square minus 3 is less than 0. I can say 2a square plus a minus 3 is less than 0, right? So this gives you what? 2a square minus 3a minus 2a minus 3. This is plus. So from here you get 2a, a minus 1 minus 3, or let me take it plus 3, a minus 1 is less than 0. So you basically get 2a plus 3, a minus 1 is less than 0. For what values of a do you think is this true? So now the basics are popping up slowly and steadily. If I talk about the number line, I can say this is a equals minus 3 by 2 and this is a equals 1. Fine. At minus 3 by 2, at 1 this will be equal to 0. So a cannot be taking these two values because I want less than 0. If you take numbers from here which are strictly less than minus 3 by 2, this will be negative, this will be negative, so the answer will be positive. So I cannot take this range. If you take from here, again greater than 1 is going to again make both these positive. So you cannot take this. So this is your very answer, that a should actually belong to minus 3 by 2 to 1 open interval for this situation to hold. Therefore, what is the range of a? It is minus 3 by 2 to 1 open interval. Moving on to the next question, let's see what we have. Fx is given as a plus b mod x plus c mod x whole square. Okay. Where a, b, c are real constants, then f dash 0 exists if. Okay, so f of x can be alternatively written as what? A plus b mod x plus cx square. There is no need to write mod x whole square. Now see, this is constant function, always differentiable. Polynomial function, always differentiable. What is the problem is this? Because mod x is not differentiable at x equals 0. So that means f dash x will be existing for x equals 0. That means f dash 0 will be existing only when this particular expression in the very function is not present. Because if this expression is present in the function, I am not going to get fx differentiable at x equals 0, or f dash 0 will not be existing. If this constant b is equal to 0, I can say yes, in that scenario this particular expression will be vanishing from the definition of my function f, and therefore my function will be becoming differentiable at x equals 0, because constant function is always differentiable, and what is this? Polynomial function is always differentiable. Sum of differentiable is differentiable. Clear? Therefore, b should be equal to 0 for f dash 0 to exist. Conceptual question. Moving to the next. Fx is given to us like this. It is saying that then the value of the pair a comma b for which fx cannot be continuous at x equals 1. Let's see. So the correct option is give me that ordered pair a comma b for which this fx cannot be continuous at x equals 1. So let's check the continuity of the function at x equals 1. Limit x tends to 1 from the negative. From the negative, if you see, it will be ax square minus b, right? Fx is ax square minus b. It's a polynomial, so x equals 1 gives you what? A minus b. And limit x tends to 1 from the positive. This is x plus 1, so it is 2. My function will be continuous at x equals 1 if left hand limit is equal to right hand limit is equal to the value of the function at 1, that is already given to be 2. But I am saying that I don't want my function to be continuous. So that can only happen, see over here what is happening is value of the function at x equals 1 is same as the right hand limit. So the only scenario left for the function not to be continuous at x equals 1 is when this right hand limit is not equal to the left hand limit. So not continuous at x equals 1 means that a minus b should not be equal to 2. When a minus b will not be equal to 2, LHL will not be equal to RHL, and hence my function will be discontinuous at x equals 1. So now 2 minus 0 is 2. For this it will be continuous at x equals 1. 1 minus minus 1, that is 2, again continuous. 4 minus 2, 2, again continuous. 1 minus 1 is not equal to 2. It is for this value of the ordered pair a comma b for which this function is discontinuous at x equals 1. Right? Next we have fx is degree of this particular expression. Then at x equals root 2, fx is what? What is the feature of fx? Now how to interpret this function? See, it's pretty easy. Fx is standing to give you the degree. Now see, if you take x greater than root 2, root 2 is the breaking point for us, right? If x is greater than root 2, suppose it is equal to root 3, then root 3 whole square is 3. 3 is going to become the degree because 3 is the largest exponent now. Rest, there is any exponent is smaller than that. So whenever x is greater than root 2, x square turns out to be the degree. And whenever x is less than or equal to root 2, suppose you take equal to root 2 whole square is 2. 2, here also it is 2, degree is 2. In fact, anything less than root 2 also if you take, suppose you take x equals 1, you get u to the power 1 plus u to the power 2. So now this is the largest, so degree is 2. So basically whenever x is less than or equal to root 2, I get 2 as f of x. Now it is saying, what is it? Continuous but not differentiable, what? The only problematic point is root 2. Let's check at root 2. Limit x tends to root 2 from the negative. From the negative it is 2. So your answer is 2. And limit x tends to root 2 from the positive, it is x square, which is root 2 whole square, which is 2 again. Right? And obviously the value of the function at x equals root 2 is also 2. So basically f is continuous at root 2. What about the differentiability? Left hand derivative, if you talk about, what do we have over here? Left hand derivative at x equals root 2, it means d by dx of, so left hand derivative of 2 at x equals root 2, this is nothing but 0. And right hand derivative at x equals root 2 is d by dx of x square at x equals root 2. D by dx of x square is 2x. 2x at x equals root 2 gives you 2 root 2, which is clearly not equal to the left hand derivative, that is 0. So the function is, yes, continuous at x equals root 2 but not differentiable at x equals root 2. So this function basically is continuous at every real number but not differentiable at every real number. So it is continuous but it is not differentiable. Clear? Next, let's see what we have. We have f is a function which is given to us to be differentiable already, such that f of x plus 2y is equals to fx plus f of 2y plus 4xy for all xy in the collection of all reals. So let's understand what is this trying to say. F of x plus 2y equals fx plus f of 2y plus 4xy. I need to somehow bring f dash in picture because every option has the expression of f dash. So somehow we need to manipulate this expression to conclude things about f dash. So here what I can say is f of x plus 2y minus f of x is f of 2y plus 4xy. Clear? Now what you do is over here you divide by 2y. Let's see. F of x plus 2y minus fx whole upon 2y is f of 2y plus 4xy upon 2y upon 2y. So this gives you what? F of x plus 2y minus fx whole upon 2y equals, this gives you 2x plus f of 2y minus 0 I can write. Why? Because what is basically given to be the function f of x plus 2y is equals to fx plus f of 2y plus 4xy. I can write it as f of 2y minus 0 upon 2y minus 0, right? So what basically I'm trying to say is, if you put x and y both to be 0, you basically get the answer to be equal to 0 itself. So what basically we get is, over here, if I apply limit y tends to 0, if I apply limit y tends to 0 both sides, what is it that I get? So limit y tends to 0 gives me f of x plus h minus fx whole upon h as h tends to 0 is actually f dash x. H is playing the role, h is being played by 2y as its role, so this becomes f dash x. This is equal to 2x plus again limit y tends to 0, right? This is f dash 0, and this is true for all x. So in particular for x equals 1 also it is true. So I get f dash 1 equals 2 into 1 plus f dash 0, or I can say f dash 0 is f dash 1 minus 2, and therefore this happens to be your answer. So somehow we just manipulated the expression to bring f dash in picture. F of x plus 2y minus fx whole upon 2y was incorporated, and then limit y tends to 0 or limit 2y tends to 0 is the same thing, was brought into picture, and hence f dash was brought into picture. And then because this is true for all x and y in the collection of all reals, therefore specifically for x equals 1, because that is what the question's demand was. So for x equals 1 we incorporated the very value of x as x equals 1 and got this as our answer. Okay, this was the discussion about the questions on continuity and differentiability. That's it from my side. Thank you.